Lesson 8.2, properties of logarithms. So first couple examples here, kind of a recap of 8.1. We got this rolling the log trick. What you used to write in terms of an exponent. Now there's a different way to write it with a logarithm. There are two different logarithm keys on your calculator. There's a base 10, and there's a base e. Okay? But what if you have some other base? Well, there are ways to work with that too. And then your book goes through some examples here that are pretty much the set of rules that I wrote down, which I'll definitely take you guys through. But let's look at the set of rules, because if you get the set of rules, then you'll be well on your way to answer these type of questions. Okay. And so first rule I get here, do they call this they have names for these, product, yeah, product property. Okay. So a logarithm of a product, that's to say two numbers multiplied like A and B, you can actually separate this out as logarithm of the first number plus logarithm of the second number. Okay. Okay, so when you're multiplying numbers, that's the same as adding their logarithms. Ooh. Okay, so that's fun. Okay. And division, well, it's probably not a huge creative leap. Is okay, if you're dividing A and B, you're taking the logarithm of that. That's the same thing as subtracting two different logarithms. Log A minus log B. Ooh, okay. I mean, these really go hand in hand. If you know one of these rules, you know the other. If you know this product rule, you know this quotient rule. Okay. How about this power looking rule? What if I have a logarithm of A to the power of B? Now, interestingly, you're allowed to take that power there, B, and pull it out in front and have B times log A. That's the same thing. The best way to learn these is to just do a bunch of examples, but it just points out. And one other rule I think will take you a long way, and we applied this a little bit in A1, or 8.1, is if you have log of any base to some or of something, so log base B of A, right? Okay, well, what if you have a weird base? Because again, your calculator only has bases 10 and E for that B place, right? But what if you have something crazy, right? Uh, well, you can take log of any base of A over log of the same base of B, right? As long as the bases match. So here I have base 10 and base 10. And the other option on your calculator is base E. So it could be ln A divided by ln B. Yeah, like natural logs. Okay. So there we go. So let's take this set of rules and just solve a bunch of puzzles pretty much. Yeah. So yeah, the first couple examples here were kind of a recap of 8.1. So let's get straight to example 3 here. Example 3. Right, product property. So say use log base 3 of 5 is approximately 1.465 to evaluate. So this is given. Okay. So find log base 3 of 405. Well, how could that be useful? Well, I wonder what this 405 has to do with this 5. Let's try that. Okay. So let's do 5 to the 3. No, let's do 5 to the 4. No, that didn't work either. Right. Um, Here. Well, maybe I'll call this. You know what? You know what? Let's do 405 divided by 5. Yeah, okay, that's what they're going with this. There you go, 81. All right, so let's do that. So I know that 405 is the same thing as 5 times 81. Okay, so I know that. So I'm going to take that and substitute right there. What we're going to do. Okay. So that's log base 3 of 5 times 81. Okay. Now I can separate these out as separate logarithms. So I have log base 3 of 5 plus log base 3 of 81, like that. Okay. Now they told us at the outset what log base 3 of 5 was. Okay. Otherwise, like, well, what do you really do with that? How do you solve that without a calculator? So that will eventually sub in there. It's something important later. But this 81, I can write in terms of 3. Okay, here's go. Okay. Because I know 81 is 3 to the something. Is it 3 to the 4? It sure is. Yeah, so this is 3 to the 4. So now I can use this right here and substitute right here. So let's try that. Okay, so this is log base 3 of 5 is equal to log base 3, or sorry, plus 3 of 3 to the 4. Okay. And here, did your book do that other rule? No? Okay. All right, so they're going to say power property for a couple examples later, but power property would be really useful right here because I can just pull this 4 out in front. Okay. Now this, remember, was given as approximately 1.465. Okay. And this here is like 4 times log base 3 of 3. All right. Oh, here's another log rule. Whenever this base matches this inside part, okay, I mean, think about what if you just saw that in isolation? Wouldn't 3 to the power of 1 be equal to 3? Like anything to the power of 1 is itself. This bit right here is equal to 1. Okay? So this 1.465 plus 4, which is equal to 5.465. Okay? This should be the answer they're looking for. Does your book say that? Uh, well, I get kind of close. Okay, but I showed you guys another way to solve this too. So we're doing log base 3. Okay, I'll switch to blue ink. So I made the claim earlier that this is the same thing as log of, let's say, natural log of 405 divided by a natural log of 3. I bet if I run this expression in my calculator, I should get the same answer. Okay, let's see if this and this match. Okay. So that's going to be the question. Is this equal to this? Okay, so let's find out. Let's do natural log of 405 divided by natural log of 3. Okay. Yeah, 5.465 about. That's it. Check, check, check. Oh yeah, oh yeah. All right, next one. Example 4, quotient property. Okay. Which is kind of, yeah, related to product property. If you get one, you could probably figure out the other. Okay, so they're saying given log base 3 of 5. Okay, so same as before, same given 1 point. So approximately 1.465. Okay, and they want us to find log base 3 of 9 divided by 5. Okay. Well, a over b, this is the same thing as log base 3 of 9 minus log base 3 of 5. You do it that way. Okay? And 9 is 3 squared. So this is log base 3 of 3 squared minus log base 3 of 5. Okay? Now, same thing as 2 times log base 3 of 3 minus log 3, 5. Okay? And then this bit right here is equal to 1. So it's the same thing as 2 minus log base 3 of 5. Okay. Okay. Now they told us log base 3 of 5 is approximately this decimal. So I can sub in right there. Okay. And then when you do 1 minus it, what's 2 minus 1.465? This should approximately equal 0.535. Okay. We're all headed towards that. Okay. Okay. Back to the beginning, my other way of doing this, because of blue ink, so this would be the same thing as, okay, so look at this right here. Okay. Natural log of 9 over 5 divided by natural log of 3. Okay. Let's see if I get the same thing down here. So natural log of 9 on 5 divided by natural log of 3. Yeah, 0.535. That's it. That's it. It's the same thing. That is that. Check, check. Bing. All good. Yeah. Yeah. Example 5, power property of logarithms, right, which we've actually been kind of using a little bit. So, right. So they gave us this, given that log base 2 of 6 is approximately 2.585. So we got that. To approximate the value of, so find log base 2 of what? 1296? 1296, something like that. Okay, what's the way to write 1296? What did you both decide? Oh, they went with 6 to the 4. Yeah. Okay. How would you know that unless you really poked around with it? Maybe you can make a factor tree. I bet, okay, if you made a factor tree, this could come out to 2 times 2 times 2 times 2 times 3 times 3 times 3 times 3. Okay, so 4 2s and 4 3s. Now 2 times 3 is 6. Okay, so that consolidates to 6 to the power of 4. Okay, so you could totally do it that way. So that'd be log base 2 of 6 to the 4 is really what we're talking about. Okay. Now, this power rule that we're doing, power property, so you take this 4 and put it in the front. Okay. Log of something to a power. The power can come out and multiply, And now it's no longer an exponent. Ooh, hey, that could be nice. Okay, like what if there was an x up there or something you had to solve for? No, you could just come out front and no longer be an exponent. That would be really nice, wouldn't it? Oh, and look at here, these. They told us this. This is approximately that. So should be approximately equal to 4 times 2.585. Let's see what that is. What's 4 times 2.585? Looking at 10.34 should be pretty good. Okay. Let me try it with the other method. So here, I'll switch to blue ink. So is this the same thing as natural log of 1296 divided by natural log of 2? Okay. We got to find out if that should match that. Okay. It's been working all along so far. Natural log 1296 divided by natural log of 2. 10.3. Yeah, it's the same thing. Yeah, 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 yeah. Oh, yeah. Oh, yeah. Winning. Uh, Example 6. Solve a logarithmic equation by using properties. We get a story here. The loudness and oh, and decibels. Yeah, that's another classic use case for logarithms. Okay. If you hear that some loudness is like 60 decibels or 50 or 70, right? How are those? Right? Like, here, guys, if you go from 30 decibels to 60 decibels, we're gonna say, oh, well, it looks like the number doubled, right? 30 to 60. Right? But decibels use a logarithmic scale. So if you're going from 30 to 60, you've increased the sound level by many, many orders of magnitude. Like 30, you can barely hear, and 60 decibels is like regular talking, right? And if you double that to like 120 decibel, I'm talking about doubling the number, not the intensity, right? But if you went to say 120 decibels, that would be on the verge of tearing your eardrums out, is what the equivalent pressure would be, because that's many, many orders of magnitude different. And so what does your book have to say about this? The loudness, L, for loudness, example 6, is equal to 10 times log base 10 of R, where R is the relative intensity. Yeah, again, you could measure this in watts. There's a similar, slightly different expression in terms of pressure. Because how do you hear? Okay, so sound waves are traveling through the air usually for our ears to hear it, or through some medium. Okay? And there's some pressure, right? So your eardrums vibrate back and forth from pressure differences, right? And then your brain can make sense of the sound and the language and whatnot. Okay. Okay. Okay, so instead of pressure intensity is slightly different. So if one person has a relative intensity of 10 to the 6, wait, hold on, oops, sorry, skip. A choir director wants to determine how many members could sing while maintaining a sound level of 80 decibels. Right? So the loudness is in dB. See, yeah, okay, loudness in decibels. Okay, so this bit right here, we're gonna let equal to 80 decibels, which is quite loud, quite loud. Okay, but okay, there'd be a choir, and okay, that can make sense. Um, if one person has a relative intensity of 10 to the 6, then how many people could sing to achieve this particular loudness? So here, I'll be going along my equation. So equals 10 times log base 10, da, 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 da. Okay. But what about this R here? Well, if it's a single person singing, then the relative intensity would just be 10 to the 6, which is a million. But what if you have two people singing? Well, that would double the intensity. So it'd be 2 times. What if you have 12 people? It'd be 12 times. Okay? And we're trying to figure out how many people. So I'm going to call it X many people. And each person has like a million value for the relative intensity that goes for right? Hey, we got to solve for this X. Okay, I think we can do that. So first thing I'll do is divide both sides by this 10 right here. I'll drop the dB and just carry the numbers. Okay, so it'll be 8 units is equal to log base 10 of X times 10 to the 6. Okay. And then let's do the roll the log trick. So 10 to the 8. 10 to the 8 is equal to X times 10 to the 6. Well, 10 to the 8 here, I'll write, so I'll expand this like 1 followed by 1, 2, 3, 4, 5, 6, 7, 8. I would read that as 100 million is equal to x times 10 to the 6 is a million. I'm just throwing an intermediate step, but you got to divide by this million value. So x is equal to 100 people. Okay, so this choir can have up to 100 people singing in it, right? Each at this intensity, this relative intensity, right? And that would produce a choir loudness of 80 decibels, and you just don't want to go over that because at some point it's just too loud. Right? You start getting noise complaints in the neighborhood right? So 100 people can be in this choir. Yeah. All right. Yeah, I did check that one ahead of time, and the teacher's manual got the same value on that. Okay, so good on that one. Okay. Book puzzles. Number 4, solve each equation. Got log base 4 of x. Just for it. Okay. Is equal to 3 over 2. Okay. So there's a couple ways I can handle this. Let me do that roll the log trick. You say 4 to the power of 3 over 2 is equal to x. That should lead you straight to the answer. 4 to the 1/2 is the square root of 4. That's raised to 3, but I'm throwing all these middle steps. But square root of 4 is 2. I think x is equal to 8. That should be that, right? Okay. How else could I solve this? I could have done this. Could have done natural log of x divided by natural log of 4 is equal to 3 over 2. Natural log of x is equal to 3 halves times natural log of 4, and then e to the power of both sides. Okay, that's another rule. Right? This e to the ln x is the same thing as x. I haven't even showed you guys this yet. I'm just doing this a completely different way. But if I plug all this in the calculator, it should tell me 8. Let's see if it does. Let's see, e to the power of 3 over 2, that'd be 1.5, and then natural log 4. Yeah, it is. It's 8. 8. Oh, yeah. 8. Check, 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 check. Number 10. Solve each equation. Check for extraneous solutions. When you see something like that, maybe like you get an answer and you say, okay, all my work is good, but then you take that answer, plug it to the original statement, and sometimes it fails for some reason. All right, let's try this out. Log base 4, 2 to the x squared minus 20 equals log base 4 of 6. Okay, so probably like domain range restrictions, I'm thinking. Okay. Because what I see here, I kind of randomly highlighted some of these. Okay, that looks good, that looks good, that looks good. But now that I'm looking at it, actually, I think these all have these in common. Is you have log base something equals log of the same base of something else. So the inside parts must be equal. Okay, so let's try that. So 2x squared minus 20 equals 6x. Well, I'm going to subtract 6x both sides. So that gives me 2x squared minus 6x minus 20 is equal to 0. Why did I do that? Because I see this is headed towards quadratic. There's an x squared and an x and a constant. So if I get it all to one side set equal to 0, I can try to factor this. Let me see. Are there numbers? Well, I'd probably need a 2x and an x if this factors. Maybe a 5 and a 4, maybe? 5. Yeah, that's what it would be. 5 here and 4 here. Because if I go negative, yeah, watch this. All right, let me show you guys this should work. If I do first, outside, inside, last, it should bring me back to the previous line. So 2x times x is 2x squared. Bing! Outside, negative 10x. Inside, 4x. Negative 10x of 4x is negative 6. Bing! And then 4 times negative 5 is negative 20. Bing! Yeah, so this does factor this way. If you were not able to factor this, you could totally bring out the quadratic equation that to the 2. But now, this times this is equal to 0. So this part could be 0 or this part could be 0. Okay, so this is 0. Subtract 4 divided by 2. X could be negative 2. Okay, because 2 times negative 2 plus 4 would be 0. Right? Or x could equal 5 from here. Because right there. Now, they did say check for extraneous solutions. So I do remember this started out as a logarithm. Remember your basic logarithm is basic log graph looks like this. Here's x, here's y. Okay. So there's this domain restriction. So I think log of something, the inside part has to be positive. Okay. Okay, that's immediately going to be a problem for -2. This would have to be extraneous, right? Because that'd be log of -12. Okay, so if I do log of -12, I know the base is different, but the principle is the same. It should say, yeah, domain error. Yeah, you can't do that. Can't take log of a negative. That makes sense. Okay. Now this 5 looks like it's working here. 6 times 5 is positive. Does it work over here? 5 squares 25, just choose 50, minus 30. Yeah, that's also positive. So there's only one answer, even though the initial algebra looked like, oh, look like there should be two solutions, but really there's only one real solution. One real solution. All right, so that's 16. Ooh. All right, so they give us some of these approximations. All right, so let's do log base 4 of 4 over 3. Okay. Well, log of a fraction, that could be the same thing as log base 4 of 4, and then minus log base 4 of 3. Okay. Log base 4 of 4 is equal to 1. That's because 4 to the power of 1 is 4 if you roll the log. Okay. And then what is this bit right here? Now here's where your book probably gave this to you. Log base 4 of 3. Yeah, it's right here. Log base 4 of 3. 0.7925. Oh, in parentheses, I'll put given. Okay, so there's one. Where'd that come from? Okay, so what's 1 minus 0.7925? Nope, nope, nope. Come on. 1 minus 0.725. So approximately, maybe I should say approximately 0.2075. Okay. All right, alternately, let's do ln of 4 over 3 all divided by ln 4. That should tell me the same value. See, it's the same value. All right, yeah, same thing. Check. All right, and I used that trick a few times to check already. Okay, so it keeps working. All right, 17. Right, same premise here. What's log base 4 of 9? Okay. Well, that could be natural log of 9. Oh, wait, what am I? Actually, you know what? They probably want you to use these here. They gave you some log base 4s, but let's do log base. Let's just stick to log base 4. Okay. I think I want to use this a different way. So that could be a log base 4 of 3 squared is 9. And of that, I could take this 2 and put it in front. So 2 log base 4 of 3. Okay. Did they give you log base 4 of 3? Oh, yeah, it's the same as before. So this part right here is about 0.7925. That's given. So put it all together. What's 2 times 0.7925? Look at 1.585. This should be the answer, right? Now, the way I was going to do it, I scratched out. I'll use that to check. It should be the same thing as natural log of 9 over natural log of 4. Right? So natural log 9 over natural log 4 is the 1.585. Oh, yeah, it's the same thing. Check. Same thing, same thing, same thing. 26. Oh, earthquakes. Back to earthquakes here. Richter scale, magnitude reading M. So 26 M as in magnitude. And so you turn on the news, say, oh, there was a magnitude 7 quake and blah, 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 somewhere today. It is given by log base 10 of x, where x represents the amplitude of the seismic wave. So x refers to the amplitude. There we go. Okay, what else here? Determine the reading of an earthquake that is 10 times less intense than an earthquake that measures 4.5 on the Richter scale. Okay, ooh, this is a good application question. Gotta stretch your imagination a little bit on this because we're comparing two earthquakes and say, okay, what's the magnitude? 10 times less magnitude. Okay? So I'll maybe I'll set up a system of equations. Let's do magnitude 4.5 earthquake for one of my earthquakes. And that could be log base 10 of some amplitude intensity, something like that. Okay. And what we want to find is what's the magnitude earthquake. So I'll say M we're solving for of an earthquake that's 10 times less intense. So whatever this intensity was, this is going to be 1/10 of that. Okay. this is basically a system of equations. System of equations. Okay. Now, I should be able to navigate this map in such a way that the exact intensity, whatever x is, kind of cancels out, although we could solve for it, but later. Okay. But what we really want to do is say, like, what is this magnitude compared to this magnitude? Okay. And regardless of what x is exactly, even though you could solve for it, you can solve this in terms of relative values. Okay. I think 1/10 of the intensity, this number should be 3.5, I think. Yeah, but let's find out. Okay. So what can I do here? Um, Let me rewrite this as magnitude equals log base 10 of x minus log base 10 of 10. I could do that. That's a valid step. Okay. And this right here is equal to 1. Okay. Also, log base 10x, that, that right there, same thing. Same thing. Okay. So the magnitude of this little weak earthquake is you take the Richter scale reading from the stronger earthquake and minus 1. Yeah, it is 3.5. All right, that's what I was thinking. Okay. So 10 times less intense earthquake is a Richter scale reading of 1 unit. Right? Again, we never actually solved for x. So what is that actual intensity? I'll tell you what it is. It's 10 to the power of 4.5. Okay. Okay, whatever units those are, that number on screen, whatever units of intensity. Okay. But regardless, even if it was like some different earthquake, okay, whenever you have 10 times the intensity, the value changes by 1. If it's 10 times less intensive, you subtract 1 from the Richter scale number. If it's 10 times more intense, you add 1. So an earthquake that's 10 times more intense than this 4.5 Richter scale would be 5.5. Hey, there you go. Now, what's next? I think I just got 3 more highlighted. So let's do this one and then these 2 stories, and then I'll wrap up this lesson here. So what do they do here? Solve each equation. Okay, so we're just back to solving. So we got log base 3 and x squared over 4 equals log base 3 of 25. Okay, this looks pretty similar to before, that log base 3 of something equals log base 3 of a different thing. Those inside values must be the same. So we'll set those equal. X squared over 4 equals 25. Multiply both sides by 4. X squared is 100. Square root both sides. Okay. I'm thinking 10. Now you might say, well, could it be negative 10? Because negative 10 being squared would also be 100. We'll check both of these. Right? Do they both work? Does only one of them work? Well, you know what? X is being squared in the original expression. So I think that actually should, actually, maybe we can do both of those. I think they should both work. Okay? Because once you square the x value, it always becomes positive. So there's not really a domain issue. Let me make sure. So if I do natural log of 100 over 4, and then divide by natural log of 3, it should, you know what? Yeah, okay. 2.93 it up, and then natural log of 25 over natural log of 3 is 2.9. Yeah, it's the same number. Okay. So I think this actually does have 2 legitimate solutions. So we're good there. Or I should say real solutions, right? 2 real solutions. Okay. 45, physics. Actually, both of these are physics. Yeah, so that's why I had to hit these. Sir Isaac Newton determined that any 2 particles exert a gravitational force on each other. He measured the gravitational force of attraction between mass 1 and mass 2 is given by, okay, so the force is equal to some constant multiplied by mass 1 times mass 2, all divided by the distance between those objects squared. Right? Yeah, so D stands for the distance between the objects. It's the center to center distance. This is mass 1. This is mass 2. This F stands for the force. Okay? And K is some constant. So I'll just call it constant. Okay? In physics, we call this capital G. I use, but your math book was using lowercase k, so I'll stick to that. Use the property of logarithms to find the expanded form of log f. Yeah, that sounds fun. So if I take log of the force, okay, that's equal to log of all this stuff. Okay? And if that's true, here, go ahead, write that. Log of k m1 m2 all over d squared. Okay. Uh, See, if you're multiplying or dividing a bunch of values, remember that's the same thing as adding or subtracting their logarithms. Yeah. So log of the force equals log of the gravity constant plus log of mass one plus log of mass two, right, minus log of d squared. Okay? Now, I can actually do one more thing. I can take this d squared, the square root of the d, and I'm allowed to move that in front of the logarithm. So go ahead and do that. Right? So log of the force between two objects is log k, log of the gravity constant, plus log of the first mass, plus log of the second mass, minus 2 times log of the distance between them. And so as they get further and further apart, right, the force gets smaller and smaller. Okay? Yeah, this would be the logarithmic expansion of the universal law of gravitation. Okay? And while you guys are looking at that, digesting that, writing that down, draw a little sketch here. So you have the Earth and the Moon. This is not the scale, but just get the idea. The Earth and the Moon. Okay. These objects have different masses, and there's a distance between them. So maybe I could call Earth mass one, the Moon mass two. There's some distance from center to center. I'm going to treat this as point masses. That distance we'll call d. Okay. And then this universal gravity constant is just some value in the universe that, well, we know what it is. It's like, here, I'll tell you guys, k equals 6.67 times 10 to the negative 11. It's a very tiny number. Newton meter squared per kilogram squared. So it's SI units, be like that. Okay. Nobody knows why this number is what it is, but it's been observed to be that, like measured to be that. Okay. So a little physics going on there. Let's do one more. Number 46, motion. Harmonic motion of a pendulum. Actually, my physics classes are just about to be starting on this lesson here. Okay, so if you have some massive a bob here, okay, and did they do, well, they say pendulum here, although there's another story this could apply to. Okay. It's like if you have mass on a spring, okay, some mass on a spring, some spring constant. Okay, you pull it down and it oscillates. Boing, 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 boing. Okay. How much time does it take? How much time does it take for this bob to swing back and forth? Call that. Well, they're calling it P for time period, so I'll just stick to that. Okay. And for the pendulum, this constant actually is Earth's gravity field, is what it is. Okay. But we got this expression. So here's the math version. So the time period equals 2 pi times the square root of. Actually, you know what? You know what? Hmm. I just realized your book kind of messed up. That's okay. All right, I'll tell you how, and it's all going to be okay. Okay. For the pendulum, the mass doesn't actually matter. What matters is the length of the pendulum. You can fit any mass bob here, and the time period will be the same. So this is time period. Okay. Now, where this equation actually is perfectly fine to use the mass here is if this k is the spring constant. All right. And you're watching this mouse on the spring, you pull it down, and boing, 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 it just oscillates. How much time does that take? Like, with the pendulum, here, maybe I'll switch to PT here. I'll put in parentheses, length, and for this K, I'll put gravity field. Gravity field. All right, whatever gravity field planet you're on. If you swap those out with the pink values, that would correspond to this picture with the pendulum. Okay, anyway, that's some physics details. So they probably want us to make a log. Yeah, that's exactly it. Use properties logarithms to write this in expanded logarithm form. So I can say log of the time period is equal to log of 2 pi multiplied by, now since I have a square root, I'm going to re-express this in terms of powers. So m for either this mass or this length, so pick your favorite, okay, to the 1/2 because that's what square root is, isn't it? 1/2. Okay. Okay. Times, and then k, which could either be, again, the spring constant or the gravity field in the case of the pendulum. Okay. To the -1/2. Ooh, because isn't it -1/2 power, like 1 over square root? Okay. So that's one way to say that, right? So then log of the time period equals log of 2 pi, which is just some constant. It's all constants there. Okay, plus, now I can bring down this, maybe I'll say that for another step. Log of m to the 1/2 plus log of k to the -1/2. Okay, and I'll do one more step here, which is take these powers and bring them down in front. This power in front, this power in front. Uh, so log of p equals log of 2 pi. Okay, well, while I'm at it, let me get an estimate on this because this is just some value, isn't it? What is log of 2 pi? It's about 0.9 or 0.798, approximately 0.798. There's a little trivia there. Okay. And then plus 1/2 log of m minus 1/2 log of k. All right, I think that will do it right there. Oh yeah. Oh yeah. Looking pretty good. All right. And that is a wrap on 8-2.